These are the solutions to the Mathematical Methods Linear Algebra exam from 2014. You'll see you have to answer all questions in section A, so you must answer question 2 and you have to answer 3 from section B. So my first question on linear algebra is question 2. For 2 part A, you want to show that these 3 vectors are linearly, well, you want to prove whether they are linearly dependent or independent. For part B is a linear transformation question. Part C, you want to find eigenvalues and eigenvectors of a 2 by 2 matrix. And part D, you want to prove that this mapping is not an inner product on V4R. So for 2 part A, we simply find the determinant of this matrix. So these vectors give the rows of the matrix. We find the determinant, and you'll see it's minus 20, which is non-zero. And because the determinant is non-zero, then these vectors are linearly independent. For part B, we want to determine whether or not T is a linear transformation. There are no modulus signs or no nonlinear terms in here, so we think that it is a linear transformation. So we have to take 2 general vectors, a u and a v, which are in P3R. So these are 3-dimensional polynomials. I want to prove that T of alpha u plus v is the same as alpha T of u plus T of v. So T of alpha u plus v is equal to this expression. So this is just simple addition of polynomials. Then we apply the mapping to this polynomial to get this 2 by 2 matrix. This 2 by 2 matrix can then be split into these 2 matrices, and then you can clearly see that T of alpha u plus v is the same as alpha T of u plus T of v, so T is a linear transformation. To find the eigenvalues and eigenvectors of this matrix, we simply subtract lambda on the diagonal to give the characteristic polynomial. So this is the characteristic polynomial. And then we want to solve this equation. So the characteristic polynomial equals 0. This does not have nice roots, so we have to use the quadratic formula. So these are the roots. And then we substitute these roots to find that the solution of a minus lambda I times a vector x is 0. So here is a minus lambda 1 I, and here is the corresponding eigenvector, which gives you 0, 0. So you'll see that these are just the negative of those 2. And the second row just takes care of itself. For lambda 2, again we subtract lambda 2 on the diagonal, and again this is the eigenvector corresponding to the eigenvalue lambda 2. For part B, we need to find a counterexample, so we just need to show that one of the axioms for an inner product fails. Now, if you take the vector u is equal to 1, 2, 2, 1, then phi of u with itself, you'll see by applying this mapping, phi of u with itself gives us a negative answer. And you'll see that axiom 3 breaks down. So phi of u with u should always be greater than or equal to 0. In this case, it's negative. So axiom 3 breaks down, so therefore phi is not an inner product. And that concludes the solutions to question number 2.